Hello and welcome back to Reciprocal and Quotient Identities, Part 2. And you see I have a snazzy example sitting here. I'm going to attempt to prove that tan theta times cos theta divided by cosecant theta is equal to sine squared theta. Okay, so what we saw last time was that we have to keep them separate. So we're going to work the left side and the right side independently and try and get them to look the same. Now along the way I'm going to give you a tip or two. So one of the tips here, okay, the first thing I always try to do is everything that's not a sine or a cosine, I try to change them into sines and cosines. So we try to convert everything, to sine and cosine. And usually a lot of the stuff unravels if you do that. So the first thing I do is I see, well, there's a tan theta here. Now tangent is the same as sine theta divided by cos theta. Okay? And then I have times cos theta. Now that's all on the top. And on the bottom I have cosecant. Well, I can use a reciprocal identity which says that's the same as 1 over sine theta. Okay. Well, let's see. What can I do? Oh, look at these cancel. The cosine on the top and the bottom here cancel. So what I now have is a sine theta on the top and on the bottom 1 over sine theta. Well, I'm going to get rid of this complex fraction by multiplying the top and bottom by sine theta. Notice that this is really important. I multiply the top and bottom by the same thing. If you don't multiply top and bottom by sine theta, then you're changing the left side, and you're not allowed to do that. On the bottom part of my fraction, this sign cancels with this sign, so I got just the number 1 on the bottom. And on the top, I have a sine times a sine. So here's what I actually ended up with. I have sine squared on the top and 1 on the bottom. And I think you'll agree that equals sine squared. So left side equals right side. So that's not too bad. Now, one thing we haven't looked at, which we must look at with these trig proofs, are restrictions. Okay, so I'm going to squeeze them down the right side here. Restrictions. Restrictions means you're not allowed to make a denominator turn to 0. In other words, I look here, for example. Here's a little fraction. I have a sine over a cos. Well, I can't let cosine here on the bottom become equal to 0. So cos theta is not allowed to equal 0. Similarly, here I have 1 over sine theta. Well, sine theta cannot equal 0. Okay, so these are restrictions. Now, I have a little bit more work to do here because this isn't telling me how to restrict theta. It's telling me that sine theta and cos theta cannot equal 0. But what restriction is there specifically to theta? So what I would do, most of the time, this is easiest if you think of the graph. Let's just do a mini version of the cos graph here. Okay, so we know cosine does this. Okay, when does cosine equal 0? Well, right here and right here. Okay, now where is that? Well, remember that the period here is 2 pi, and that means this is pi in the middle. So this is half of pi. And this is 1.5 pi. So what I'm getting from this, sorry, I'm kind of running out of room here, is that theta cannot equal half of pi plus 1.5 pi's plus the next one that comes along. So a quick way to write all that is to say pi by 2, which is this guy here, the starting point, and saying every time we add pi to that, we hit 0. So plus multiples of pi. So those are the no-no zones. Okay, pi by 2 plus any multiples of pi. I'm going to be hitting zeros along this graph here, and that's not allowed. The other thing, and I think I can squeeze it in here, is the sine graph. When is that restricted? Okay, well, when sine is equal to 0, and that's going to be at 0, at pi, and at 2 pi, and 3 pi, and so on. So multiples of pi. That's the other restriction. Okay, so that is the business of restrictions, and sometimes they ask for it, and sometimes they don't. However, know how to do it. Okay, next example. Next example I'm going to try to prove is this. I'm going to try to prove that, cosine of x divided by 1 minus cos x. I'm going to try to prove that that equals 1 divided by secant x minus 1. All right, well, first tip that I gave you was try to convert everything down to sines and cosines. Well, the left side here is cosine, so that's pretty good. So let's leave that alone. What about the right side? Well, secant is the same thing as 1 over cosine. So that's the first thing I'm going to do is change that. Then I'm going to look at this and say, oh boy, how do I clean up this mess? Actually, it's not too bad. So what I'm going to do is I'm going to multiply the top and bottom by cos x. And that way I'm going to get rid of that fraction. Okay? Notice it's top and bottom multiplied by cos x. So on the top, I would have cos x times 1. And look what I get on the bottom. I get cos x times 1 over cos x, which is 1. And then I get cos x times negative 1, which is negative cos x. And I go, oh, so you're saying left side equals right side. And yeah, pretty easy proof. Now, what about restrictions? Okay, restrictions. Okay, let's look for any denominators. Can't let them equal 0. So, here's a denominator. I can't let that become 0. In other words, I can't let cos x equal 1. Okay, so that's one of them. And then, oh, here's a fraction. I got a 1 over cos x. So I can't let cos x equal 0. And I think that covers all of my denominators. Now, cos x not equaling 0, we actually just saw that one in the previous example. That means pi by 2 plus multiples of pi. So those are the bad zones there. What about when cosine is 1? Cosine is 1, again, if you think of the graph, really helps. Cosine is 1 right here at the start of it and right here at the end of it. So it seems every time I start at 0 and I add multiples of 2 pi, I've got 1. So multiples of 2 pi is the zones best avoided. All right, I think that's where I'm going to stop for today. So we're going to catch you later with some more